Hi everyone at Dynamics Workshop. My name is Yang Yu. I'm a PhD student from Royal Institute of Technology of Sweden. Today, I'm here to present you work by me, Mihail Miratis, and Elena Dubrova. The title of our paper is called Why Deep Learning Makes It Difficult to Keep Secrets in FPGAs. Here's the outline for today's presentation. First, I will give you a brief background on the several notations that appears in our work. Then I'm going to introduce you the adversary model as well as the attack scenarios. The third section is about experimental setup and results. And the final part is the conclusion and a short discussion. As many of you might know that every chip is slightly different from each other due to the manufacturing process variations. And the physical clonable functions, which are abbreviated as puffs, accumulate this kind of variations and enables us to create a fingerprint of each individual chip. That makes the puff a cost-efficient way of both generating and also storing digital keys. So the output of the puff, which is also called the response of it, is random in the sense that no one knows its value before the chip is fabricated. The puff generates responses only when the chip is powered on, which means the attack on the puff has to be done while the chip is running, which is the opposite to, for example, the fuses, whose content can be read from a power-off chip. If the chip is tampered with, the responses of the puff are most likely to change, which makes puff also a tamper-resistant way in hardware security. For those who do not know about side channel leakage, side channels are sources of information in addition to what was anticipated or defined in a security model. As you can see the graph on the slides, the leakage is outside the computation process, and it is a result of the side channel, and it can enable considerably more powerful attacks than conventional ones. So the side channels produce leakage information of varying complexity. It can be scalar, for example, the overall execution time, the error message, or the 4D ciphertext. It can be vector or trace form. So, for example, the cache hit or miss, power consumption, electromagnetic emission, or packet size. As the aspect of the operating environment, it can be noisy or not noisy. It depends on the type of the leakage, certain amount of effort is needed to target and explore it. Nowadays, with the help of machine learning, the attackers can deal with even more complex and noisy leakage information. As the FPGA's forename Field Programmable Gate Array suggests, the FPGA is an integrated circuit which is designed to be configured by the customer or the designer after manufacturing. The FPGA's architecture is shown on the slide and consists of the following main parts. The CLB stands for the configurable logic blocks, which performs complex combinational functions or some simple logic gates function. And the S stands for the switch box, which perform the routing and interconnecting functions, and some input and output interfaces. Here is a detailed look inside the CLB tile, which consists of several LUTs, which stand for the lookup table, which performs the logic function, and multiplexer and a bunch of flip-flop which perform as a register. So the user defines the function it wants the FPGAs to implement using hardware description languages. The tools provided by the FPGA's manufacturer convert this code to a hex file, which is also called the bitstream. And the bitstream is used to configure the FPGA and tells the FPGA what to do and what resources it wants to use. The bitstream's format is proprietary and secret, which motivates the reverse engineering. There are certain common rules when the tools create a bitstream. Take the 6-input dual output LUTs as an example. It converts as a 64-bit initialization vector split into 4 16-bit parts, and each part in a fixed distance from each other. So the main steps of a LUT-based attacks are: the first step is to map a target function into possible LUTs and write them in bitstream format. The second step is to find the LUTs that implement the target function in the bitstream. The last step is to modify the content of the LUTs that found in the previous step. Besides the LUTs content, the attacker can also target on the connections, which inspire new types of bitstream modification attacks. And why this is so important? Because in a FPGA as a service setting, the user cannot keep neither the bitstream nor the data protected from the hardware owner. The adversary model of our paper is the following. We assume that the adversary has a physical access to both the JTAG or select map configuration interface and the bitstream of the FPGA under attack. We also assume that the adversary has equipment for power analysis and expertise in power analysis, deep learning, and bitstream reverse engineering. Note that in a FAAS setting, the hardware owner satisfied all the requirements described above. Our paper takes the following two different attack scenarios into consideration, and none of it requires the attacker any knowledge about the buff design. So the first attack scenario, the victim buff has a constant placement, while in the second scenario, the buff is frequently configured. And in both cases, the attack steps are: first, the attacker needs to retrieve the bitstream from the victim FPGA, then add the extra flip-flops through bitstream modification, and then load the modified bitstream onto the profiling FPGA and train the classifier. The last step is to load the modified bitstream onto the victim FPGA and perform the attack. Please note that the victim FPGA can be the same one or a different one. On the slides, you can see a snapshot of our experimental setup. It consists of 1 chip per Pro and 4 FPGA boards of 2 different types. The chip per is a hardware security evaluation toolkit, which is based on a combination of open source hardware and also supporting tools. So the chip Pro on the left down corner is a capture hardware. It is used to measure power consumption over the shunt resistor placed between power supply and FPGA chip of the target device. And the chip Pro also communicate between the target device and the computers. In order to evaluate the results of our attack, we choose to perform it over the arbiter path. To some of you who might not know about the arbiter path, here's a brief illustration. So the arbiter path consists of several switch blocks, which are controlled by the challenge bit to perform either parallel or cross paths. And the pulse input creates a race between two symmetrically designed paths and can accumulate or small manufacturing differences in delays. And a D flip-flop, which works as an arbiter at the last to produce 0 or 1 response corresponding to which path arrives the first. We have tried many different neural networks architecture, but here's the one that we decided on at last. It consists of one input layer size 150 and one 1D convolutional layer and one average Prolin layer and one flattened layer, was connected to 3 fully connected dense layer and one output layer. Other specifications you can find on slides as well. At first, we tried to use the neural network to train on the power traces from the conventional APUF and get the validation accuracy around 0.58, which is exactly the number of the mean of the responses of the puff, which implies the model does not learn anything from the power traces. And you can see it from the left figure of the slides. That is the result before the submission of the paper. After that, we do more exploration on these traces. We use the average traces for the same challenge, which means we capture 100 traces for the same challenge and use the average traces as the training set. This do increase the validation accuracy up to 0.73, but that still is not a satisfying result for us. Then we come up with the idea of combining the deep learning based side channel attack with bitstream modification attack. And it means that we add n extra F flip-flops between the arbiter and the output to magnify the power consumption of the response bit. Here's the experimental results. In the table, you can see the expected number of traces required to recover the APUF response with 100 accuracy for 100 tests using FPGA 4 for profiling. All of the implementations are generated by code except the last one, which we manually modify the bitstream to add the 50 extra flip-flops. But you can see from the last two rows, they're of the same level in numbers. And considering the time that we spend on manually modification, we try to use the generated implementation to save time. Then we try to attack the protected arbiter path. In our work, we attack on the protected arbiter path whose challenge are encrypted by the advanced encryption standard core. Here's the comparison of the unprotected path and the protected path. And you can see the numbers are in the same level, which means the attack can still work on the protected APUF as well. For attack scenario 2, where the puff can be reconfigured from time to time. We try the following experiment. On the slides, you can see the layout for the FPGA, and the APUFs part is colored orange. So the placement 1 is where the APUF is occupied the one straight column, and placement 2 is APUF where it occupies several columns. Here's the result of using placement 1 for profiling. So for attack scenario 1, we get the left table as the result. For attack scenario 2, we get the right table for results. As you can see that for the same amount of extra flip-flops, the scenario 2 definitely need more traces than scenario 1. And for extra flip-flop less than 200, we couldn't get the attack work within 1,000 traces. Despite the fact that you need definitely more traces and more extra flip-flops, our attack still works in attack scenario 2. We presented an attack which can classify responses of an arbiter buff implemented in FPGA, even encrypted. And this implies that puff-based key provisioning methods may not be secure in a hardware-owner-controlled environment such as FAAS. We choose puff to present the attack doesn't mean that this kind of attack only applicable for puffs. And more efficient attacks can be made on other FPGA implementations of cryptographic algorithms by combining deep learning-based side-channel attacks with bitstream modification. We hope to attract more attention to this type of combined attacks in order to intensify research efforts on designing suitable countermeasures. Thank you for your participation. Do you have any questions?